Okay, welcome to example number 6. We have a spring mounted horizontally on an air track, and with the left end held stationary attached here. We attach a spring balance to the right side, and we pull with 6 newtons of force, and notice that it displaces a total distance of 0.03 meters, so 3 centimeters. Then we remove the spring balance, and we attach a 5 kilogram mass, and we pull it a distance of 4 centimeters, so 0.04 meters, and then we release it and watch it oscillate sinusoidally back and forth, exhibiting simple harmonic motion. And so we're asked to find a number of things. Okay, so first thing is to find the spring constant, and that's where the first picture comes in. So we're going to need to find out the force constant. So we knew that when x was equal to 0, when x was displaced to a distance of 3 centimeters, or 0.03 meters, we knew that the force by the spring would be 6 newtons. And it would be in the negative x direction because we're pulling force to the left, pulling to the right, and the spring would be exerting a force to try to restore it back to the left. So if we use Hooke's law, Fs equals negative kx, we have negative 6.0 newtons equals negative k times the displacement of 0.03 meters. That will give you a spring constant of 200 newtons per meter. Okay, the next question is asking for what is the maximum and minimum velocities attained by the vibrating object. So when this oscillates back and forth, we want to know when it is going the fastest. So hopefully you realize that when this object moves back and forth, it's going to be the fastest when all of the spring potential energy that would be stored at the endpoints here is converted into kinetic energy, and no longer any of that energy is into spring potential energy. So we're going to use an energy approach. Alright, we know that the total energy of the system is made up of kinetic plus spring potential energy. So the total energy is given by 1/2 Ka squared, and then the maximum kinetic energy is going to be equal to 1/2 mv squared, and that's going to occur when the spring potential energy is 0, because that occurs when the displacement is 0 and there is no spring potential energy. So to find the maximum velocity, we're going to rearrange this equation, and so that we have spring constant over m in the square root multiplied by the amplitude, and then substitute our numbers. We had the spring constant of 200 newtons per meter that we got in part A, divided by the mass of the object, which is 0.5 kilograms, and then multiplied by the amplitude, which is 0.04 meters, and that gives you a maximum velocity of 0.8 meters per second. So that's the maximum. What's the minimum? Well, the minimum is the same amount, but it's just basically negative. And you might be wondering, well, where does that occur? Well, it occurs at the same place, x equals 0. It just depends on when the object was passing through. So when this object was initially going through here and passing through and moving to the left, then we had maximum. That was actually the minimum velocity because that is going towards the left direction. When it reaches the endpoint over here and then turns around, then comes back going in the other direction, then we have a maximum velocity to the right. So we're interpreting the minimum velocity as really the most negative velocity. Okay, let's go to part C. It's asking for the maximum and minimum accelerations. So we need to find something that relates the acceleration to the known information. Well, we're given the displacement, and we also know that the acceleration is directly proportional to the displacement. So if we can find some relationship that relates the acceleration to the displacement, that would be great. Let's try to derive it here. We have F equals ma, and then we have negative kx equals ma, and so we can see that A equals negative k over m times x. So to find the maximum acceleration, that is going to occur when we find the minimum displacement. So we really want x to be a negative value. So we're going to have negative of the spring constant, which is 200 newtons per meter. the mass is 0.5 kilograms, and the displacement is going to be negative 0.04 meters. Now, so that's going to be occurring when the object is over here. We're going to be having that spring force pushing it to the right, trying to restore it back to the equilibrium, which is over here. And so that's going to create a maximum acceleration when it's to the furthest point to the left. That gives you an acceleration of 16.0 meters per second squared. So you might be asking, well, where is the minimum acceleration? The minimum acceleration will be the same amount, except it will be basically negative 16.0 meters per second squared. And this occurs at basically x equals positive 0.04 meters. So when the object is right here released from the right side, the restoring force is acting to the left and creating a maximum acceleration to the left, which is the minimum acceleration. Okay, part D is asking for the velocity and the acceleration when the object is halfway to the center, somewhere in between here and here. So that's when x is equal to half of the amplitude, which is really 0.02 meters. Okay, so to find the velocity, we're going to go back to a very similar method that we used in part B. We're going to use conservation of energy. The total energy of the simple harmonic oscillator is made up of kinetic and spring potential energy. The total energy is 1/2 k times a, which is the amplitude, squared, plus, or this is equal to 1/2 mv squared plus 1/2 kx squared. Now the difference between this method and the previous method now is that x is not 0, x is 0.02. So it's going to have partly kinetic and spring potential energy, and we're going to be solving for the velocity. So we have 1/2 times, say, the spring constant, which is 200 newtons per meter, times the amplitude, which is 0.04 meters squared, equals 1/2 times the mass, which is 0.5 kilograms, times the velocity we were trying to solve for, plus 1/2 times the spring constant, 200 newtons per meter, and we have the distance is now half the amplitude, which is 0.02 meters squared. And so when we solve for this, you'll get a plus or minus of some square root, and I don't know what that is, but when you plug it into your calculator, you should get negative 0.69 meters per second. We chose the negative because when the object is at half of the amplitude, it is moving to the left. So that's why we have a negative velocity here. Okay, we also need to find the acceleration. Now earlier we defined the acceleration. Let's just use this equation over here and just use the same method, except we're now going to be plugging in for a different value of x. So the acceleration at that particular point in time will be negative 200 newtons per meter divided by the mass of 0.5 kilograms multiplied by the displacement of 0.02 meters. And that will give you an acceleration of negative 8.0 meters per second squared. So you'll notice that it's half the acceleration at that half the displacement. However, is the velocity at that point half of the maximum velocity? No, it isn't. So remember that even though it's at half the position here, it's not half the velocity. That's because you can see there's a v squared term in there. Okay, we have part E now to answer, and that is the kinetic energy, the potential energy, and the total energy at that halfway position. So let's go ahead and do that now. So part E, the kinetic energy is defined as 1/2 mv squared. So 1/2 times the mass, which is 0.5 kilograms, times the velocity, which is negative 0.69 meters per second squared, and that gives us a kinetic energy of 0.12 joules. Let's now calculate the spring potential energy. The spring potential energy is 1/2 kx squared, so it's 1/2 times k, which is 200 newtons per meter. Remember, x is half the amplitude, which is 0.02 meters quantity squared, and that will give you an energy of 0.04 joules. And the total energy you can calculate by doing 1/2 Ka squared. So 1/2 times 200 newtons per meter times 0.04 meters squared. And that gives you a total energy of 0.16 joule. Do you notice something when you look at these two energies? Does the kinetic energy and the spring potential energy add up to the total energy? Yes, it does, and that should make sense because energy must be conserved. And just a quick reflection on this, you'll notice that when we had to calculate the acceleration, we couldn't use any kinematics equations because the acceleration is oscillating. It's sinusoidal. Alright, so you can calculate the acceleration, the velocity, the position, the force. All those can be related to one another, but you can't use kinematics equations because the acceleration is not constant. And that's it for this example.